Welcome back. Today's section is 6.1, estimating area under a curve. The essential question for today, how can I use rectangles to estimate the area underneath the curve? Before we actually do this, I've got a couple of problems right at the beginning. This one says, Mr. Anderson ran down the hall at a rate of 3 feet per second. How far did Mr. Anderson run during the first 4 seconds? So this is a pretty easy problem to solve. If I was traveling for 4 seconds at 3 feet per second, 4 times 3, I've traveled 12 feet, right? 4 seconds, 3 feet, every one of those 4 seconds equals 12 feet. The interesting thing is if we actually graph the curve of my speed. So this graph is linear. I called it a curve. It is technically a curve. It's just a linear curve. So this is showing me I'm traveling at a constant 3 feet per second. So there's my velocity. And if I traveled for 4 seconds, we can find the area underneath the curve, because area of a rectangle is base times height. You will notice the base of this curve has a unit in seconds. So the base is 4 seconds. The height of this rectangle is a measure of velocity. It's measured in feet per second. So that height of 3 is 3 feet per second. So you might have noticed already, if I wanted to find the area of that rectangle, it would be 4 seconds times 3 feet per second. Seconds times feet per second. The seconds cancel out. I just end up with the units in feet. That's 12 feet. If I have a velocity function, the distance I traveled over a certain amount of time is the same as the area underneath that velocity function for those number of seconds. So since I traveled for 4 seconds, I just found the area of the rectangle from 0 to 4 seconds. That area is in units, 12 feet. Like that's finding actually the distance I traveled over those 4 seconds. Now this seems kind of like, why would I ever do that? Because I found it was 12 feet up there without ever needing this graph. But it turns out if your speed wasn't constant, right? If I started going 2 feet per second and then I sped up to like, what is that, 3.5 feet per second, and then I slowed back down, if I had a velocity curve, I could still find the distance I traveled by finding the area under that curve. So you are now starting the second part of calculus. Calculus has 2 main branches. The first talks about finding slopes, which is called derivatives. We found derivatives, we spend a lot of time with that. The second part is going to be finding area. Now we are going to find area underneath the curve using calculus. We're going to find exact area. We're not there yet. So for now, all we're going to do is we're going to estimate the area underneath curves. So that is the goal today. Today's goal is to use rectangles to estimate the area underneath the curve. There's 3 main ways I can do that. All of them are called rectangular approximation methods, or RAM. The first one looks like this. One way to estimate the area under a curve is by drawing rectangles that all touch the curve at their upper left-hand corner. So I'm trying to estimate this area right here. And I'm doing it by drawing a bunch of rectangles. Now it's not going to be a perfect estimate. You can see that I missed some area here, I missed some area there, and I've got too much area right here. That's an overestimate. But overall, it wouldn't be a bad estimate of that area, right? So when you draw rectangles whose left corners touch the top of the curve, that is called LRAM, standing for the left-hand rectangular approximation. That's not the only place I could draw rectangles though. I could do the same type of thing, but I could connect my rectangles where their right corners is touching the curve, right? So this first rectangle, the right corner touches, then the right corner touches, then the right corner touches, etc. That would also estimate the area under the curve, a slightly different estimate. Right, this time I'm overestimating here and here, too much, right? I'm too much above the line there. I'm underestimating here, but it averages out. So again, this is estimating this area under the curve. It's estimating that area. And it'll be a pretty good estimate. A little bit of overestimate, a little bit of underestimate, but it averages out. If you use the right-hand corners of rectangles, guess what it's called? RRAM, for right-hand rectangular approximation. The third one, instead of connecting the corners, we connect the midpoints of each rectangles to the curve. That would be called MRAM, for connecting the midpoints. All three of those are different ways of using rectangles to approximate the area underneath a curve. All right. What if we want a more accurate approximation? So here I'm using 1, 2, 3, 4 rectangles, and it's not, I mean, it's a good approximation, but I've definitely got a couple of underestimates on the left here and here. I've got an overestimate there on the right. It's a pretty decent approximation because that overestimate is going to kind of counteract some of that underestimate. But I think overall, it looks like I'm going to be a little bit too small with my estimation, right? There's definitely more of an undercount than an overcount there. If I want a more accurate approximation with rectangles, is a pretty easy solution. Use more rectangles. When I use more rectangles, the size of those underestimates becomes less, right? Because the more rectangles I use, the closer I'm going to get to touching the actual curve. So in my overestimate, that's really reduced, not nearly as much of an overestimate. So if you want a better estimate, just use more rectangles. All right, let's do a couple actual problems. All right, this first problem is asking me to estimate the area underneath the curve from x equals 2 to x equals 8. So there's 2, there's 8. So I'm trying to estimate this area here underneath the curve. I want to figure out how much area is there. I'm using 3 rectangles for my estimate. And so the first thing to identify is this an LRAM, RRAM, or MRAM approximation? You don't really need to know that to find the approximate area, but you really should know it to figure out what to name it. So take a look at that, see if you can name it. All right, if you said LRAM, you are correct, because each of these rectangles touch the curve in their upper left-hand corner. So this is an LRAM approximation. To find the approximate area, we just add up the area of those rectangles. This rectangle appears to have a height of 5 and a length of 2. It actually has an exact height of 5, but we'll talk about how I can figure that out later. So that's an area rectangle of 5 times 2, right? 5 times 2, that means that has an area of 10. This rectangle has a height of 6, width of 2. 6 times 2 is 12. And my last rectangle has a height of 5 again, and still a width of 2. 5 times 2 is 10. So then add all those up. 10 plus 12 plus another 10 is an approximate area of 32. I don't have units on this, so I'm just going to say 32 square units. All right, next problem. Same curve, still this curve, still from 2 to 8. So I'm approximating the same area, but I'm using more rectangles, so my approximation should get more accurate. Again, identify if this is LRAM, RRAM, or MRAM. All right, this one is RRAM because it's the right-hand corner of every rectangle that's hitting the curve. So since that's RRAM, good to go. Finding the approximate area is still finding the area of each rectangle. This rectangle is a little harder though, because I look here, I'm like, how tall is that exactly right here, right? It looks like maybe 5.5. So in calculus, if it doesn't say just estimate the height, you're gonna have to do more than estimate. You gotta find that exact height. Luckily, we've got an equation here. That equation tells me the value of y for any x I put in. Well, if I want to know the height right there, put a 3 in. I'll land right on the curve at that point. So putting a 3 into this equation would be negative 0.25 times 3 squared plus 2 times 3 plus 2, which is 5.75. So this first rectangle is 5.75 units tall times a width of 1 which is just going to be 5.75. All of these rectangles have a width of 1, so it's all, every area is just going to be the height of each of those rectangles. But then to find the next rectangle's height, you just plug a 4 in, the next rectangle's height, plug a 5 in, next rectangle's height, plug a 6 in, etc. Since I'm going to do this repeatedly, it would probably be a lot easier to do this with a calculator. So I'm going to show you that really quick, and then we'll find the approximate area. All right, here's my curve that I was given, negative 0.25 x squared plus 2x plus 2. We already found what the height was when I plugged a 3 in, but with Desmos, you can do it pretty easily by just doing f of 3. There it is, 5.75. You want to find the height when you plug a 4 in? Do f of 4. It's 6. What about a 5? 5.75. And you can do that for as many different values as you like, and then you can add them together to find your total area. All right, so here we are. That first rectangle had a height of 5.75 times a width of 1. The second rectangle had a height of 6 and a width of 1. And then another height of 5.75, etc. Add all those areas up, and I get a total area of 28.25. There is my estimation of the area under the curve using RRAM. Now that is the same curve again as I did before, but since I used more rectangles, it's going to be a more accurate approximation. That's it. There are 6 problems to do this. There's a couple of notes. The instructions on this assignment weren't too clear from what I remember. So some important notes for number 10, I want you to use 4 rectangles. Find both the LRAM and the RRAM. So if the instructions aren't clear, just follow that. Here are what you should get for answers. For 19A, the book expects you to average the LRAM and the RRAM. So find the LRAM, find the RRAM, add them together and divide by 2. I'm not sure why it didn't make it clear that's what it expected you to do, but that's what they expect you for your answer for the 19A. All right, I'll see you later.